Evening, everyone. My name is Stephen Martinez, and I'm the new chapter president for the North Texas chapter of the AMS NWA, and I'd like to welcome you all to our first meeting of the season. So I'm here. I don't know. This is muted. We're okay.
Yeah, I think it says unmute.
Yeah. No, we're okay. Yeah. So so I'm here. I have with us Stanley Christmas. He is our treasurer. Dave McAnally, he is our secretary. He's the one running the Zoom show. And I don't know if Greg is here with us. Greg Higgins, he is our vice president. So without further ado, I'm just going to straight up turn over to Dr. John Nielsen-Gammon, who I've got to work with a few times in the last few years. But more importantly, he is one smart cookie in the field. He got his PhD at, I see that eye roll. He got his PhD from MIT. He's been working as a professor at Texas A&M since 1991. He's also the Texas State climatologist. He is a Regents professor at the Atmospheric Science Center, the director of the Southern Region Climate Center. He's also a fellow of the American Meteorological Society. And everything climate that deals with Texas, rainfall, temperature, and the drought monitor that we've all gotten familiar with recently over this summer all runs through him. So it's great to have him on board. Dr. Nielsen-Gammon, the floor is yours.
Okay, well, thank you very much. Let me first say happy to be here, at least virtually. And I was originally going to talk about something else, but we kind of noticed that North Texas has had some interesting rainfall recently, so I thought I'd focus on extreme rainfall in Texas. And I don't usually accept the graphical suggestions of Microsoft, but I was amused that when it had a title of extreme rainfall, that decided to come up with rainfall rate of 1 foot per 10 seconds, which is probably a bit excessive, but it's definitely eye-catching. So, outline of the talk. First off, just briefly touch on the extreme rainfall that occurred in the DFW Metroplex last month. I'm not going to go into the mechanics of it. Y'all have lived through it, probably are more familiar with the particular event than I am. Then I'm going to talk about something where it was really extreme, like Hurricane Harvey, and the amount of precipitation that happened there. And lastly, I'll talk about how extreme rainfall is changing across the state and across the southern United States. So here's a Kocaras plot of the rainfall distribution during basically the 48-hour period from the morning of the 21st to the morning of the 23rd. So that spans the heavy rainfall period. Decent coverage in the area. We're missing a bit along the inner suburbs of Dallas. Tarrant County has good coverage. Picked up one observation with 12 plus inches. Three more in Dallas, including over at Belt Springs, where the heaviest flooding seems to be. Managed almost a foot in northeastern Ellis County, 10 inches in southern Coppin County. And overall, an eye-catching rainfall event, and was touted as, I don't know what the numbers were. Certainly, it exceeded a 1 in 100-year event. Typical, basically for that area, the 100-year rainfall, which is the amount of rain you'd expect to see once per century on average, is about 9 to 10 inches. By the way, if you have any questions, just unmute yourself and speak up. A small enough group that we can be nice and interactive here. So anyhow, how historic is this event? Well, it's historic for the places that got 12 to 15 inches, but on a broader scale, here are the 10 heaviest single-day rainfall events in in north central Texas, and it doesn't make the top 10. Number one is one of my favorite outliers, the 29 inches in one day in Albany, Texas, remnants of a tropical storm drifting through the area. That basically was, I don't know. I don't know if anybody's ever actually estimated the odds of getting 29.05 inches in a particular location in west central Texas, but it's probably somewhere along the lines of 1 in a million. I'm serious about that. I'm probably not exaggerating. The next value, which is a bit more reasonable, was the Corsicana rainfall from 2015. And there were 11 stations that picked up more than 10 inches of rain in a single day in that event. The one that hit the biggest number of rain gauges was back in September of 2010. That heavy rainfall was mainly around the area between Temple and northern Austin, with the highest total being about 14 and a half inches. We can go to page 2 and finally pick up the one here in terms of the single day total. Highest was 11.3 from Cocoras. Of course, you could find higher totals if you look at the flood control networks or pick your optimal 24-hour period. But the same thing applies to all these other events also. So it wouldn't be a fair comparison to dig deeply into one and see how it compares to the standard information from the others. So what we can say is this was a moderately rare event, but it was obviously especially unusual for the location where it happened, where it could have some of the maximum impacts. The good news is not as big an impact as if you'd gotten 29 inches in one day. That would have been fun. Okay, and Cocoras is great for providing lots of gauge data coverage. But you know, these numbers are nice, but they aren't as nice as the numbers we saw during Hurricane Harvey. And the heaviest recorded totals were in Jefferson County in that case, which is the extreme southeastern corner of the state. So what I'm going to do is take advantage of a uniform gauge network by the flood control districts in the area. There's actually 2 that have quite a few gauges. The green numbers are with Drainage District 6. The blue stations are Drainage District 7. And it just so happens that's a smaller network, and it also includes the heaviest totals. So what we're going to do is get a sense of how much variability there is from station to station in this larger network, and then apply what we learned in order to identify suspicious values in the smaller network and see if those high totals actually fall under the suspicious category. And this is a fun thing to do here, not because you're interested in Southeast Texas, but because it's a very weather nerdy type thing to see what observations look like and how good observations can go bad, so to speak. So one way of comparing is to look at the correlation between the hourly rainfall totals among adjacent stations. So this is a plot of the correlation between stations that are separated by the specified distance in kilometers. And you expect that a single station will be perfectly correlated with itself, which we observe. You also expect that the farther away you go, the less correlated the stations will be, because individual rainfall event will hit one station in 1 hour, maybe another station in a different hour. But as long as you're within a few kilometers, it ought to be pretty consistent. So this is the pattern we got during Hurricane Harvey. This is probably more consistent than it would be during a typical, say, air mass thunderstorm type event, because at least you had stuff organized in rain bands, so that 2 stations that are far apart could still experience the same rain band at the same time, potentially. Now, the open circles are the stations that ended up surviving our quality control checks. And the other ones in various colors are the ones that didn't. And in this plot, you can see one of the distinctive aspects of the ones that didn't is they disagreed with their neighbors to a unusually large extent. I suppose the one that stands out is this one down here, which is just in a complete world of its own. That's obviously bad. But these others are doing things like having a correlation of 0.7 with a station that's less than 5 kilometers away, whereas the expected value is more like 0.95. So let's look at a few of these and see if we can figure out the failure mode, why the correlations might be less than expected. So let's start with the 3 stations that are in this maroon circle here within Beaumont proper in Jefferson County. And I'm plotting the hourly precipitation values for the 3 stations. And in this plot and in the other ones, the thick graph is the station that's suspicious. And in the latter part of the period, hey, they all look pretty nice. They all have similar amounts at similar times. But in the early part of the period, the gray station is basically underestimating peaks, and also, at least for this peak, it's not ending it promptly. The same, you can see the same sort of thing down here. So the way that this could be generated is if there's some obstruction at the orifice of the rain gauge, like a bird's nest or something that is basically trapping the rain and letting it dribble through. And what we surmised happened was that right about 2 in the afternoon on August 28th, the maintenance guy came out there and cleared out the gauge. There's the spike as the remaining water drains in, and after that, it's doing just fine. So we saw that at another station that also got cleared out, apparently about an hour later. And there were a couple more stations that showed this sort of thing developing that didn't get fixed. But this is a nice contrast between what you expect almost co-located stations to look like if they're working right, and what it looks like when they're not working right. Okay, here's another failure mode. Now we're looking at the stations up here in the northern part of Jefferson County. I've plotted about 9 stations, and some of them failed our check and some of them survived it. And looks like they're all doing fairly consistent with each other early on, but you notice the color patterns sort of change at the end. Let's zoom in on that latter period. And what we see is that this gauge suddenly zeroes out. And then this gauge suddenly zeroes out. And this gauge suddenly zeroes out. And then this one suddenly zeroes out. And then this one zeroes out. Turns out those 5 gauges are the ones that are closest to Pine Island Bayou, which forms the northern border of Jefferson County. And so the expectation for this failure mode is basically the water along the bayou is getting high enough that it's flooding out the gauges. And this one got flooded out first, and it got flooded out second, and so forth. And we spotted that because, well, the correlation is great up to this point. Correlation is lousy afterwards, and so the overall correlation doesn't look as good as it should. Now, so it's one thing to check if the gauge is responding properly to the rainfall. It's another thing to check if it's got the right calibration, if you're responding to the correct extent. So we can check that by looking at basically the regression slopes. If you know the rainfall at one station, how accurately would you be able to predict the rainfall at another station? Are they consistent? If they are consistent, the regression slope should be 1. Same amount of rain at one station should correspond to the same amount of rain at the next one. Now, as you go farther away, the expected correlation decreases because the differences get larger. This is, by the way, using 6 hourly rainfall totals, so we minimize the timing issue and look at more at the calibration issue. And here, the yellow dots pass our quality control. The blue ones do not. And let's take a look at an example of improper gauge in this instance. So the 3 gauges in this circle, the one in the middle is the one that fails. That's the one in orange. And basically, inexplicably, every single 6-hour period, except for one, it's reporting less precipitation than gauges either to the east or to the west by a factor of 1.5 to a factor of 2. It actually seems like it's getting worse as time goes on. So that's just a very large difference compared to what you'd expect for gauges that are within 10 kilometers of each other. You would think that basically the correlation, the slope difference would be only about 20% or so, rather than a difference of 40 or 50%. All right, so we've looked at correlations, we've looked at slopes. Let's move on to Drainage District 7, where the rainfall of interest occurred. And now in this case, I've again plotted in yellow the stations that survive our quality control, and in other colors, the stations that don't. And unfortunately, there's a few stations that don't here. No, the correlation check worked out fine, but it's this slope check, magnitudes, that don't seem to work out too well. So let's look at the 6 stations in this oval. And what we see basically is 3 categories of stations. One category, high values, one category, medium values, and one category, low values. There's 2 stations in the high group, there's 3 in the middle group, and there's 1 in the low group. Now, we could potentially believe this if the stations in the high group were next to each other, but they're not, unfortunately. They're the westernmost station and the second easternmost station, and their stations in between are in the middle group. So the only way that could happen consistently like this is, well, actually, I don't know a way that it could happen consistently like this. We might be able to double check the radar to see if the radar has large variations in amounts in that region. But otherwise, I can confirm that this middle group is also consistent with the stations at a larger radius, and it's consistent with the rainfall amount recorded at Jefferson County Airport, which happens to also be within this circle. So the tentative conclusion there is that these 2 stations are biased high, and this station is biased low, and the other ones are doing a decent job. Now, how do you get a high bias with the gauge total? Well, that's a good question, actually. It's conceivable that there's water dripping into the gauge from overhead equipment. That's a possibility. Somewhat less likely during high wind conditions, like a tropical storm. It's possible the gauge orifice isn't perfectly flat, and maybe it's tilted into the prevailing wind during Hurricane Harvey. Maybe. Maybe it's just not calibrated properly. Maybe it's windy enough that there are spurious motions of the tipping bucket, although that would happen even when it's not raining. So that's not really a satisfactory explanation. So unfortunately, unlike those other failure modes, I don't have a failure mode for this one other than perhaps poor calibration. But another look at how it's an outlier is this plot, which compares the difference in slope between a given station and neighboring stations. And our two high values are these outliers. The ones biased low are these outliers. And they really do look like outliers compared to the rest of this reasonably well-behaved normal distribution. And I mentioned radar-based rainfall totals. Well, this is thanks to Steve's work in analyzing the rainfall during Harvey. We were lucky enough to have this high-resolution data set. And we're further lucky enough to have that data set put together independently of this particular set of gauge observations, so that it is indeed an independent check. And I've plotted the storm totals here, starting at 35 inches. This is why I just smile when you say that Dallas had a heavy rainfall event recently. The dark blue corresponds to 50-inch estimated rainfall totals from the radar. And what we see in this area is rainfall estimated values around 40 to 42, which is consistent with that middle cluster of gauges. And there's not any extremely high values in the radar estimates anywhere in this vicinity. So I think that's the final nail in the coffin for the 60.58-inch total that has previously been accepted as the highest individual storm total and highest hurricane total in the continental United States. Now, that's really a bummer. So we really need to find out what is the highest total. Now, in this plot, I've circled all of the gauges what we regard as being bad. The highest remaining gauge is this 49 inches, which is consistent with the radar. So at least we made it to a storm total of 49 inches in Jefferson County. But there are other places that also got decently high totals. And what I've plotted here are values from the various flood control networks, and actually basically anything that went into an overall compilation of rainfall totals for the hurricane. It does not include some other stuff that I have access to, which is all the data from Weather Underground and Earth networks. But these are the fun ones, and in the white are all the totals that are above 45 inches. And you can see that, well, this is a decent contender for wettest totals, but we also have this band that occurred across like from Clear Lake up into Liberty County to possibly have some high totals. And the radar itself is located somewhere down here, so maybe some of these totals are underestimated because we're sort of in the cone of silence of the radar. Well, at any rate, these are what the totals come out to. So first off are the two that I just defeated through quality control analysis. Those 60-inch totals are wrong. Next up is a backyard gauge of 56 inches in Friendswood. That's over here, and it's surrounded by values between 36 and 43 inches. So that, and not consistent with the radar, so that seems bad. Next up, 54.77 inches, which is this total down here, which happens to align with the maximum radar estimated precipitation. So that's a candidate for highest rainfall total. Let's look at that in more detail. So here's a photo of the guy's backyard that made the observations. So quoting from his email to the Houston-Galveston office, I attached my raw data and a chart in Excel that shows the rainfall I measured during using two different gauges in the backyard separated by 16 feet during the 4 days Tropical Storm Harvey was harassing us. Throughout the rain event, I monitored both gauges and they were almost identical with rain measurements. Recent news articles suggest this area, including Santa Fe, Dickinson, and League City, only received around 40 inches total of rain. This is not correct. I'm confident my house received in excess of 54 inches during the 4-day event. Is it possible I was the only one that was crazy enough to monitor rain gauges in our area during the storm? I know my gauges will not qualify as certified readings, but I still feel very confident they're accurate based on past history of using them. Further detail turns out to say that this particular gauge had a smaller capacity. It actually overflowed 3 times, but the times it didn't overflow, it agreed with the other gauge. And my only other comment on this, aside from the fact the exposure seems very good, is that, boy, this seems like an awfully steep roof line. On the other hand, it probably came in handy because it allowed Harvey's rainfall to drain off quickly without accumulating on the roof. Anyhow, that total down here, yeah, it's higher than the 40 some odd inches in other areas, but it's sort of consistent with a 52 and a 53 here and a 47 here, and you'd expect it to be higher. So that could be, as long as you're willing to accept a jerry-rigged backyard gauge system, the highest rainfall total reliably measured during Harvey. Now, if you don't like backyard gauges as reliable, we can go down the list and find some other candidates. This one here is the nearest Kokoros, 49.31. That's up here in Liberty County, except that gets a footnote too because that gauge overflowed. So the observer estimated the value using a tipping bucket gauge from his neighbor. Then we can go to the Harris County Flood Control District, which was this is back at Jefferson County, 49.25 inches with the highest total observed there. If you want something that's actually part of an official network that's archived in the CEI, got it down to 47.52 for the Beaumont Port Arthur airport observation. So take your pick as to the highest rainfall total observed during Harvey, as long as your pick is not 60 inches. All right, on to part 3, which is trends in extreme precipitation. So we expect precipitation trends to increase in general with a warmer atmosphere because of the Clausius-Clapeyron equation. Warm air has a greater capacity for water vapor. And climate models are very consistent in basically globally simulating an increase in extreme rainfall of about that amount, and an amount that's definitely higher than the amount by which total rainfall is increasing on average. But that thermodynamic mechanism, as we call it, is only one of the things that affects extreme rainfall trends. It's possible that climate change can affect storm structure. I mean, if you've got more intense condensation, more intense latent heat release, you could get different sizes and shapes and intensities of thunderstorms or hurricanes or MCSs and so forth. And you might also have climate change altering the weather patterns so that storms come along more frequently or less frequently depending on location. So it's not a guarantee that extreme rainfall would increase here or there, depending on where you are, even though it should increase on average globally. And if you aggregate it over, say, the entire eastern half of the United States, you can clearly tell that there's a trend. But if you try to just look at individual station trends, it's pretty noisy. There's quite a bit of variation from one station to the next because we're talking about extreme precip. And so you only have one data point every year for the annual maximum rainfall. And potentially, the eastern United States is a pretty big area. Do we expect the rainfall trends on the Gulf Coast to be similar to the trends near the Great Lakes, for example? I don't know. So one point of this research was basically to see how precisely we can actually pin down the historical trends and how small an area do we need to aggregate over before we get a trend estimate that is reliable and has a decently small confidence interval associated with it. So we're battling signal, and it's a signal versus noise battle here. We're trying to extract as much signal as possible and beat down the noise by expanding the data. We want the longest record possible. You might think that having extreme rainfall values in the 1890s is not too useful for pinning down the trend due to climate change, because most of that trend's happened in the past 40 or 50 years. But it really is useful because it pins down what's the early value before things started increasing, what would have been expected before the globe warmed. So the way we create long records is essentially create a composite record of extreme precipitation in each county by using the longest serving station in each county and then filling in the gaps with the next longest serving station and so forth. And counties in this part of the country are small enough that you can sort of interchange them that way within the county pretty easily. We also want lots of data. So just an individual county trend would be kind of noisy, but if we aggregate them into regions, we expect to have the similar climate influences on them, then we might be able to more accurately estimate trends. And then to get a really robust trend, we want to aggregate all of these estimates across a larger geographical area. So sort of a three-step process there. And so the results for at least looking at expected values without a trend, this is showing how much rain you'd expect to see on the wettest day in a 2-year period on the left, and on the wettest day in a 100-year period on the right. And I mentioned Dallas-Fort Worth area was around 9 to 10 inches. That shows up here also. The closer you get to the Gulf Coast, the higher the expected amounts are. And that's true for the more frequent 2-year values also, which the expected value is about 4 inches in the Dallas-Fort Worth area and about 5 or 5.5 inches around Houston. So the wettest day in a given 2-year period is typically going to be around 4 inches. Now, so that's the county composites. Now, if we aggregate by region, we start getting much more geographically consistent information than we got here. You can see this is still noisy, but by aggregating by region, we're getting things that are pretty darn consistent from place to place. For the 2-year totals and the 100-year totals. 100 years a little bit noisier because it's a bit rarer, but even some of the noise is probably real. Like this region having a higher expected value aligns with the eastern part of the Balcones Escarpment, where you got flash flood alley, you got extra lifting topographically. And the same thing applies to this region in northwestern South Carolina as a possible enhancement. I find it interesting that Georgia seems to be protected by Florida. They get less heavy rain in Georgia compared to surrounding states, and that's pretty consistent across regions. Perhaps that's illustrating the importance of tropical storms in producing those really high totals. Now, recently, NOAA came out with its own estimates for intensity of extreme rainfall, and they're actually pretty consistent with ours. You can flip back and forth, and there's not much difference by eye. We subtract them, you see that our numbers tend to be lower than the NOAA Atlas 14 values. And the reason for that, at least based on what I think is going on, is that we're taking a single set of values for a single station in each county, going for the whole period of record, whereas NOAA Atlas 14 is using as much data as possible, as long as there's a decent record for an individual station. And we have more stations during the latter part of the period than the earlier part. So that means because of climate change, if there's an increasing trend in extreme rainfall, NOAA Atlas 14's estimates will be centered more in the latter half of the period than in the earlier half, whereas our data records are going to be centered more near the middle. And consequently, we'll be coming up with lower estimates than NOAA Atlas 14 will. The big exception for that is along the eastern coast of Florida. And that's basically a flaw in our method because we're picking the longest stations, which are right along the coast. And it turns out there's a pretty big gradient in the expected value of extreme rainfall as you go inland in Florida. So our values are basically the coastal values, whereas NOAA S14 is really estimating the value on average in this area. Oh, that's fine. Now let's look at the trends. And to quantify the trends, first off, these aren't linear trends. We assume that and we actually check this and it's consistent with the data, we assume that the trend is that we're looking at is whatever component is being driven by global warming. So we're actually looking at the change in extreme rainfall as a function of global mean surface temperature as simulated by climate models. And it's pretty noisy by county. It smooths out a bit if you look by region, but it's still a lot noisier than our estimates of extreme rainfall itself. The trend is more of a derived quantity, so it's more subject to noise. The way we're quantifying the trend is as a percent change between 1980 and 2020. And that's pretty decent estimate of how rapidly things should be increasing because we've seen basically a fairly steady increase in global temperature over that period. So it gives you an estimate of the current rate. Plus, as it turns out, 1980 is about the time in which the estimates that we get, just assuming no climate change, equal the estimates we get allowing for a trend. The horizontal line crosses the sloping line throughout the year 1980. So this is in turn showing how much the current risk of extreme rainfall is underestimated by using the stationary approximation, ignoring climate change. And it varies from place to place, from a little bit like -5 to as much as plus 35%. But I argue even that spatial variation is unreliable. We don't expect climate change to amplify extreme rainfall in eastern Texas, but not western Mississippi, for example. There's no reason for that to happen. Or eastern North Carolina and eastern Texas and not eastern Florida, for example. So we think to extract the climate change signal, you really have to average over a larger region. So that's what we did. Looking at the whole region, the trend in 2-year rainfall and 100-year rainfall, 2-year rainfall trend is about 7% over that interval. 100-year rainfall is about 11% over that interval. And the 95% confidence intervals all exclude 0, which means we're detecting a trend and just focus on the green dots. The other ones are looking at truncated data sets to see if that really matters much. And no, it doesn't really matter much. If you just focus on the Gulf Coast region, the same thing. Trend detected, about the same as the overall average. Southeast, that's a smaller area in our analysis, and so the confidence intervals are much larger and they include 0. So Southeast is too small. Gulf Coast is large enough to get a reliable trend estimate. So 11% trend in amount means that the 1-day total in 2020 that you should expect to have a 1% probability of happening in any given year, that 1-day total would be 11% higher than the similar expectation in a climate corresponding to 1980. And 11% doesn't sound like much if you frame it in terms of amount, but in terms of frequency, what that's saying is that the amount of rain that you would expect to have happen only 1% of the time in 1980 is now expected to happen almost 2% of the time. The odds almost double. That's how much an 11% increase in magnitude means. So that wait another decade or so, and we will be in the doubled frequency. Flooding risk, or at least heavy rainfall risk, twice as large as it was half a century ago. So summarize, we've got widespread positive trends in extreme precipitation across the southern United States. By the way, this paper just got submitted to Journal of Hydrometeorology last week. Hopefully it'll survive the review process. Otherwise, you can just forget about everything I said today. As I mentioned, 11% increase in amount corresponds to an 80% increase in frequency, which means that the flooding in Dallas is kind of rare now, but we'll see what happens in the future. By the way, the official NOAA analysis for extreme rainfall amounts came out in 2018. It includes Hurricane Harvey, which was a really exceptional event. So that probably overestimates the odds of heavy rainfall, even though it doesn't include climate change. Whereas in the rest of Texas, including Dallas, the official numbers do actually underestimate the risk due to climate change. And Harvey, unfortunately, it wasn't really a 5-foot event. It was only a 4.5-foot event. And lastly, as you can tell, I like lots of data. So thanks for your attention. I'll be happy to answer questions.
Dr. Gammon?
Yeah.
Yeah. My name's Stanley Christmas. I'm retired weather service. Back in 1978, I went to Albany the day after the rainfall event. And we did a bucket survey, and I really believe that 29 inches was real. I never saw so much devastation in my life. And what happened was the remains of a tropical system just parked over Albany that night. And it just rained and rained. So anyway, I just want to kind of throw that out. I really think that it is a legitimate amount of rain.
Yeah, thank you for doing that bucket survey. That's one of the reasons we believe it. That people actually went out and said, yeah, gee.
Right.
Well, thank you very much for the presentation. Is there any other questions here in the room, or?
Dr. Gammon?
Yeah.
Yeah, we've got a gift certificate for you for $25 for Amazon that we'll be mailing you. And thank you very much for your talk.
Okay, well, thank you very much for the gift certificate.
Yeah. So I don't know if there's any other questions online. I actually have a couple of questions, since a lot of this is up my alley. First, I guess with the slide you have up right now, how many of those events were tropical cyclone related, and how many were just, warm, efficient rainfall events here across North Central Texas in that top 10, top 20 list?
Well, that sort of depends on how you draw the line. For example, the Corsicana event, that occurred a day after the remnants of a hurricane that had made landfall on the west coast of Mexico had moved across. So it was, I think, I would not call it a tropical cyclone event, except the remnants of that tropical cyclone cranked up the precipitation efficiency for it. So it was sort of a contributing factor in that regard. I haven't done the one-by-one analysis of all these to figure out which ones of these are tropical cyclones. Certainly some of them aren't, particularly the ones in early and mid-spring. But it's probably going to be something like maybe half of them are tropical cyclone related. I don't think it's going to be much more than that.
Okay. Yeah, I think I recognize one of the dates on there that might have been, was it Hermine in 2010, kind of just dumped a foot of rain across the area?
Yep.
Yeah, so it was interesting, though, what kind of distribution there is. The second one might be a little bit more technical question from a bureaucratic point of view. So officially on record, you have that 60 inches in Jefferson County as the rainfall total. Are there plans to retract that and then reaffirm what the new total might be for Harvey, or is that? Is that process going to happen, or how would it go about?
Well, I don't know how NOAA will handle it, but when I do get a chance, we're going to write this up and send it in for publication also. I've already had 2 students graduate out from under me that were working on it and never quite got it finished. So at least in the scientific literature, if this analysis is accepted, the total will go down to 54.77 perhaps, or maybe 49.31. I don't know what NOAA would like to accept for that, but that'll be, I would say, NOAA's problem at that point.
Okay. Yeah. I know looking at those totals and what you examined on here is challenging to figure it out, just because those co-cross gauges are only, they can only handle 11 inches. And, at some point you got to dump them and keep measuring. And, so more often than not, you see overall totals ending in 0.0 or half an inch, just because they're rounding or estimating it. So I can imagine it's quite a challenge to figure out what actually fell there on the ground.
Yep. And and this is with a storm with widespread heavy precipitation over an incredibly dense network. So it's sort of sobering as to how little we know what's actually happening in all the other events as well, and how just because you got a rainfall total that's high doesn't mean it's anywhere. Doesn't mean that it's A, accurate, or B, anywhere near the highest total.
Yeah. Cool. Thank you. Any other questions? Questions in the room? No. Cool. Dr. Nielsen-Gammon, thank you so much for joining and presenting for us today, this evening. So we really appreciate it. I appreciate it. And it's good seeing you again.
Yeah, good to see you.
So just to wrap up the meeting for chapter business. So we'll meet next month. We'll meet at the Council of Governments building, which is only a couple miles away from here in Arlington. I believe the speaker we will have lined up will be from the River Forecast Center. I will verify that soon. Membership, if you would like to join or continue being a part of the North Texas chapter, there's a link online with the North Texas chapter page for a membership form to send to Stanley here and to mail to him. So if you want to be a part of that, it's only $10. So if you want to be a part of the chapter, that would be great. And I don't know if there's anything else you guys want to tackle. Cool. All right. With that, our first meeting of the year is adjourned. Thank you all for being here, and we'll see you all next time. Thank you very much.
Thank you, Doctor. Thank you, everyone.
Thank you.
Welcome. Those of you who are still on, I'll just mention one other anecdote with respect to the Albany rainfall total. It took more than one attempt to get the Albany total to survive the automated quality control in NCDC, now NCEI. We finally got the flag set so that no matter what quality control says, this is a real value.
Sometimes you do what you got to do, right?
Yep.
Thank you all.